The walls that surround us, in homes, offices, historic centers, and new buildings, are most often made of two ancient yet eternally modern materials, brick and concrete. One was born from fire and clay thousands of years ago. The other is a product of the industrial era, artificial stone whose invention revolutionized architecture. At first glance, they serve the same purpose, to provide a strong, durable barrier and support. But in practice, the choice between them determines everything. Construction speed, wall thickness, the indoor microclimate, the project cost, and even its architectural appearance. Why are multi-story skyscrapers constructed from concrete, while cozy cottages are often built from brick? Can one be considered a substitute for the other, and what is the fundamental difference between individual materials and monolithic mass? In this article, we will examine brick and concrete at the molecular and technological levels, compare their strengths and weaknesses, and understand why in modern construction they are not so much competitors as reliable partners, creating the framework of our civilization. The strength and all subsequent properties of brick and concrete are determined by their composition, which is fundamentally different. Brick is, for the most part, a product of the processing of natural clay. The raw material for the most common ceramic brick is low-melting clay, often with added sand to reduce shrinkage and prevent cracking. These additives act as a kind of skeleton, maintaining the shape of the brick during drying and firing. After firing at temperatures of 800 to 1000 degrees Celsius, the clay particles sinter, vitrifying the surface, and the material acquires the properties of artificial stone, strong yet porous. It is this controlled porosity that gives ceramic brick its most important consumer properties, the ability to breathe and relatively low thermal conductivity. Modern technologies make it possible to create highly efficient porous ceramic blocks, in which wood shavings or polystyrene foam beads are added to the clay mass. When fired, they burn out, leaving closed pores within the material, which dramatically improve the thermal insulation properties, bringing brickwork closer to the thermal performance of wooden structures. Sand-lime brick is different in nature. It is made from a mixture of quartz sand, approximately 90%, lime, approximately 10%, and water. Its strength is achieved not by firing, but by a chemical reaction between the lime and the silica in the sand, under the influence of high-pressure saturated steam in an autoclave curing. The result is the formation of durable calcium hydrosilicates, similar to some natural minerals. Sand-lime brick is very dense and compressive, but has higher thermal conductivity and a smaller variety of shapes and textures compared to ceramic brick. It is also more hygroscopic and is not recommended for foundations and basements that are constantly exposed to moisture. Concrete is a composite or complex artificial stone. Its fundamental difference is that it is formed directly on the construction site or at a precast concrete plant from a mixture of components. The basis of concrete is a binder, which is almost always Portland cement. This is the product of firing a mixture of limestone and clay, marl, at approximately 1450 degrees, followed by fine grinding. When mixed with water, a complex chemical reaction, hydration, occurs, transforming the cement paste into cement stone, which binds all the other components into a monolith. These components are called aggregates, fine, sand, and coarse, crushed stone, gravel. They form a rigid mineral framework that bears the main loads, prevent shrinkage deformations, and significantly reduce the cost of the material, accounting for up to 80% of the mixture's volume. The third key component is water. Its quantity is strictly measured, as excess water reduces strength and insufficient water makes the mixture inoperable. Thus, while brick is a single material, clay or sand with lime, transformed into stone in a factory setting once and for all, concrete is a complex ready-made formula that is transformed into stone on site. Its properties can be fine-tuned over a very wide range by varying the cement grade, the type and size of aggregates. Expanded clay can be used for lightweight concrete or basalt crushed stone for particularly strong concrete, and by introducing specialized chemical additives, plasticizers for workability, hardening accelerators or retarders, and air entraining agents for frost resistance. This fundamental difference in the origin of strength determines all subsequent differences in application. Brick is a prefabricated, standardized design element, while concrete is a technology for creating a monolithic structure of virtually any shape and size. from a flexible garden path to a load-bearing skyscraper column. The path from raw material to finished building element differs dramatically between brick and concrete, determining their economics, environmental friendliness, and final consumer properties. Brick production is a multi-stage, energy-intensive, but well-established process. For ceramic bricks, it begins with clay extraction from quarries. The clay is delivered to the factory where it is aged for freezing and weathering, then crushed and mixed with additives, sand, ash, to form a homogeneous plastic mass. Next comes the key stage, molding. There are two main methods: plastic molding. The wetter mass is extruded through the die of a belt press and then cut into individual bricks, and semi-dry pressing. The mass with lower moisture is pressed in molds under high pressure. The molded green bricks are sent to drying chambers where they are dried at temperatures of 70 to 150 degrees for several days to remove most of the moisture. The final and most critical stage is firing in tunnel or ring kilns at temperatures of 800 to 1000 degrees. Irreversible physical and chemical changes occur here. The clay sinters, acquiring a rock-like strength, color, and frost resistance. The process from clay to brick takes several days. Sand lime bricks are made differently. A prepared mixture of sand and lime is pressed, giving the brick its shape and initial strength. The green bricks are then placed in an autoclave, a sealed chamber where they are treated with saturated water vapor under a pressure of 8 to 12 atmospheres at a temperature of 170 to 200 degrees. Within 8 to 12 hours, hydrosilicates synthesize, and the brick achieves full strength. This process is faster and more energy efficient than firing, but requires complex equipment. The production of concrete and concrete products is a process separated in time and space. It can be divided into two streams: the preparation of the concrete mix and its molding into a structure. At a concrete plant, BRU, or directly on the construction site, the components, cement, sand, crushed stone, water, and additives, are precisely dosed. Then everything is fed into a concrete mixer where it is thoroughly mixed until a uniform consistency is achieved. The finished mix is not yet concrete, but concrete mix that must be placed. The subsequent process depends on the intended purpose. For monolithic construction, the mix is delivered to the site by truck mixer where it is placed in pre-prepared formwork, the mold of the future structure, compacted with immersion vibrators to remove air and left to gain strength. Strength gain is a lengthy chemical process of cement hydration, lasting weeks and months. Although the design strength is achieved in 28 days under normal conditions. To speed up the process, precast concrete products are cured in chambers. To produce concrete blocks, foundations, walls, partitions, the mixture is placed in metal molds compacted with vibration and either steamed for rapid strength gain or left to harden naturally. Thus, brick production is a closed-loop process at the factory, resulting in the finished product. Concrete production essentially involves the delivery of a semi-finished product, mixture, the final production of which, its transformation into stone, occurs on-site in the form specified by the engineer. This gives concrete incredible flexibility but requires strict adherence to production procedures on-site. The choice between brick and concrete in a specific project is determined by the balance of their physical and mechanical properties. Each material has its own strengths and weaknesses that must be considered. Compressive strength is a key parameter for load-bearing structures. Here, concrete has a clear advantage. Concrete grades, e.g. to B25, B30, can achieve very high compressive strength, allowing for the construction of columns and slabs that can withstand enormous loads in multi-story buildings and bridges. Brick also has sufficient strength, M100, M150, M200, but it is lower than that of heavyweight concrete. However, for low-rise construction, up to 3 to 4 stories, the strength of high-quality brick is more than sufficient. It is important to remember that concrete is extremely weak in tension, and this problem is solved by combining it with steel reinforcement, reinforced concrete. Thermal conductivity and thermal capacity are critical parameters for a building's comfort and energy efficiency. Brick, especially modern hollow or porous ceramic blocks, is a leader here. Due to its closed air pores, it has low thermal conductivity, meaning it retains heat well in winter and coolness in summer. A wall made of this material is already a good thermal insulator. Heavy concrete with granite aggregate has high thermal conductivity, quickly transferring and absorbing heat. A wall made of monolithic concrete without additional insulation will be cold and may freeze, requiring the installation of a thermally insulated facade, ventilated or wet. On the other hand, the high thermal capacity of concrete and solid brick walls allows them to accumulate heat, smoothing out daily temperature fluctuations inside the building. Frost resistance, F, is the ability of a material to withstand freeze-thaw cycles without failure. Modern grades of both brick and concrete, F50, F100, F200, offer high frost resistance, sufficient for most climates. However, for brick, this parameter is directly related to its water absorption. The more moisture it has absorbed, the greater the risk of failure during freezing. Therefore, brick facades require proper water repellency or cladding protection, water absorption, and vapor permeability. Ceramic brick can absorb significant amounts of moisture, up to 12 to 14% by weight, requiring protection of structures from direct and prolonged exposure to water, such as proper waterproofing of basements and roof overhangs. Concrete, especially dense concrete, has lower water absorption. Brick has a higher vapor permeability than dense concrete. This means a brick wall better regulates indoor humidity by allowing water vapor to pass from the inside out, promoting a healthy indoor climate. Concrete walls are less vapor impermeable, requiring a well-designed ventilation system. Fire resistance, both materials are non-combustible and rank among the highest fire safety classes. However, brick, being a fired product, can withstand direct exposure to open flames for longer without losing its load-bearing capacity. Reinforced concrete, when exposed to high temperatures for long periods, loses strength due to the breakdown of the cement structure and dangerous expansion of the reinforcement, requiring special fire protection measures. Thus, brick wins in comfort, eco-friendliness, and aesthetics, but falls short in absolute load-bearing capacity and construction speed. Concrete wins in strength, flexibility of form, and speed of constructing the supporting frame, but requires additional costs for insulation and is more difficult to create a comfortable microclimate. The evolution of construction has led to a natural division of influence between brick and concrete. Their use is determined not so much by competition as by the optimal match of the material's properties to the task at hand. Brick has found its niche in areas where uniqueness, aesthetics, a comfortable microclimate, and human scale are important. This applies primarily to low-rise residential construction, private homes, cottages, and townhouses. A brick wall is ideal here. It provides good thermal and sound insulation, regulates humidity through vapor permeability, and has high thermal capacity, creating a stable and pleasant microclimate without sudden temperature fluctuations. In multi-story construction, brick is widely used for infilling external walls and constructing internal partitions in buildings with monolithic or precast reinforced concrete frames. It is lighter than concrete panels and provides better insulation. Thanks to a huge variety of colors, textures, and formats, clinker and ceramic bricks are premium materials for facade finishing, lending a sense of solidity and individuality to any building. Brick is also indispensable for special structures. Fireclay bricks are used for laying stoves, fireplaces, and industrial furnaces. Concrete is a material for large-scale, load-bearing, and engineering applications where strength, speed, and the ability to create monolithic forms of any configuration are essential. Nearly all types of foundations, strip, slab, pile, and grillage, are now made of monolithic reinforced concrete, the most durable and resistant to loads and soil impacts. Load-bearing columns, stiffening cores, and interfloor slabs in skyscrapers and residential complexes are always made of monolithic reinforced concrete. It allows for open floor plans and withstands enormous vertical and horizontal loads, including wind and seismic loads. In infrastructure, concrete is unrivaled. Bridges, overpasses, tunnels, hydraulic structures such as dams and locks, runways. Specialized concrete is used wherever maximum strength, durability, and performance in aggressive environments are required. Furthermore, the concrete industry produces a vast range of products for mass construction: panels for prefabricated houses, foundation and wall blocks, curbs, and paving slabs. Cellular concretes, such as aerated concrete and foam concrete, occupy a special niche. These lightweight, thermally insulating materials compete with brick in the low-rise wall construction segment, offering faster laying times due to their large block formats. However, they lack absolute strength, environmentally friendly raw materials, and aesthetics, as they require a protective finish. Thus, a clear principle has emerged. Concrete creates the skeleton of the building, its load-bearing frame, foundation, and floors, while brick forms the body, the enclosing walls, partitions, and outer shell, responsible for the comfort, aesthetics, and final appearance of the structure. In modern construction, these materials are not mutually exclusive, but often work in tandem, complementing each other's strengths. Practical aspects of construction, time, money, and the required skills often become decisive factors when choosing between brick and concrete. The speed of construction varies dramatically. Monolithic concreting, especially with modern sliding formwork and concrete pumps, allows for the construction of entire floors of a multi-story building in a matter of days. This is a conveyor belt method, where the processes of reinforcement, formwork installation, concrete placement, and curing are cyclical and well-established. Bricklaying is a fundamentally different piecemeal process. Even an experienced mason's speed is physically limited. Mortar must be applied, the bricks laid, their positioning verified, and the joints tied. Erecting the walls of even a small cottage takes weeks. However, it's important to consider the final time. The rapid installation of a monolithic frame does not yet constitute a finished building. Afterward, equally time-consuming work on insulation, facade finishing, and interior planning follows. A brick wall, especially one made of facing brick, often forms a complete structure, requiring no additional exterior finishing, saving time during the finishing stages. There's also the issue of seasonality. Monolithic work at sub-zero temperatures requires additional cost to heat the concrete, while bricklaying in winter is highly undesirable due to the risk of mortar freezing. Comparing costs is a complex multifactorial calculation where the cost of the materials themselves is only part of the equation. The cost of brick, especially high-quality ceramic or clinker brick per cubic meter of wall, can be higher than the cost of concrete for monolithic construction. However, this price already includes strength, appearance, and thermal insulation properties. A concrete frame itself may be more economical, but it generates a whole host of additional mandatory costs: the cost of formwork, rental or purchase, reinforcement work, insulation, and a ventilated facade or plaster system. When evaluating the overall estimate, the difference is often evened out, and the final price depends heavily on the architectural complexity of the project and regional prices for materials and labor. Labor intensity and required skills also vary. Bricklaying is a highly skilled manual labor, an art form that directly affects the strength, geometry, and aesthetics of the wall. Masonry errors are difficult and expensive to correct. Working with monolithic concrete is rather an engineering and technological process, requiring the coordinated work of a team including reinforcement workers, concrete workers, and riggers, as well as strict laboratory and process control over the quality of the concrete mix and its placement. Errors here are also critical, but of a different nature: technological violations that can lead to catastrophic consequences for the entire structure. Thus, brick places high demands on the skill of the individual constructor, while concrete demands the organization of the process, the accuracy of calculations, and the qualifications of the engineering staff. The choice of one material over another often comes down to the availability of resources. In some regions, it's easier to find a good team of masons, while in others, a proven monolithic construction technology with the necessary equipment is needed. For a private developer, brick may be more understandable and easier to control at every stage, whereas monolithic work requires the involvement of a specialized contractor with extensive engineering support. Now you know that directly contrasting brick and concrete in search of a definitive better material is pointless. The comparison shows that they are not competitors, but two fundamental tools in a builder's arsenal, each designed for its own purposes. Brick is a material of comfort, aesthetics, and unique perfection. It forms the body of a building, providing heat, sound insulation, a healthy microclimate, and the final appearance. Its strength lies in creating durable, environmentally friendly, and aesthetically pleasing living environments in low-rise construction and as infill for frames. Concrete is a material of strength, scale, and technological flexibility. It creates the skeleton of a structure, the supporting framework, foundations, and critical engineering structures. Its strength lies in its ability to assume any shape, withstand enormous loads, and enable the incredible speed of construction of complex structures. Modern construction has long abandoned the either-or choice. Its logic is based on synergy, A monolithic reinforced concrete frame provides strength and speed, while brickwork or modern ceramic blocks creates warm, breathable, and beautiful walls. Thus, the brick versus concrete debate gives way to the formula concrete plus brick. Understanding the unique properties of each material allows us not to choose between them, but to intelligently combine them, creating buildings that are simultaneously strong, quick to construct, warm, durable, and aesthetically pleasing. The truth, as often happens, lies not on one side or the other, but in their strong union.